Hello dear students. So group theory is the topic that we were doing. After the definition and some basic examples of group, now we are able to differentiate between infinite and finite groups. Infinite groups having infinite number of elements. Some of the examples are group of integers, rational number, real number, complex number under the operation of addition. These are the infinite groups. Also they are abelian because they are commutative under addition. Infinite group which are non-abelian, they are the group of matrices because matrices are not abelian under multiplication. We can here write multiply because A into B is not equal to B into A in matrices. So this set of matrices form are the groups which are non-abelian but infinite. On the other hand, we have finite groups, like one of the example that we have earlier done. So this is the abelian group, and the non-abelian group, if we have to give the example of non-abelian but finite group, that is the group of symmetry or group of permutation. Now today we are going to talk about the group of matrices under multiplication. So generally we divide the group of matrices in two categories: general linear matrices of order n and special linear matrices of order n. So G for general, L for linear, and n for the order of the matrices that we will take in that group, and all the entries should be real number. So special linear group that we will define later. Now first of all, general linear group, what is this? This is set of all the n cross n matrices which are invertible, or you can say n cross n invertible matrices form the general linear group, whereas special linear group we have n cross n matrices with determinant equal to 1. So this is special case. Here the determinant, because these are invertible, means determinant is non-zero because the matrix has inverse if and only if the determinant is non-zero. So here the special case, special linear group, means the determinant is equal to 1. So all the n cross n matrices whose determinant is 1 form the special linear group. How they form? Now we are going to check these. So first of all, talking about general linear group over R. So these are the set of matrices such that A is of order n cross n and determinant of A is non-zero. Right? This is the definition. Now we are going to check the four properties of being a group. So first of all, closure property for which we have to take two elements from this set, and we have to check whether their product, because we have taken the binary operation, the product of matrices. So A into B will belongs to general linear group. Why? Because if A, B are of order n cross n, then A into B, the order of A into B is also of order n cross n. Moreover, if determinant of A not is equal to 0 and determinant of B not is equal to 0. Why? Because these are the elements of this set. So this set contain all the matrices whose determinant is non-zero. So A, B both are in this set, means both have determinant non-zero. And what is the determinant of A into B? This is nothing but the product of determinant of A and determinant of B. And these both are not equal to 0. Therefore, the determinant of A into B is not 0. So both these two conditions allow A into B to be the member of the set. Its order and determinant. Both conditions are satisfied, therefore it belongs to, and therefore closure property hold. Now the second property, associative law. This is first one. Now associative property, for which we have to take three elements from the set. Now we can see the product of matrices. If we change the order of the bracket, that the answer remains same. We don't need to check it here. Which is true for matrices, you can write which is true for matrices, right? Now come to the third property, which is existence of identity. So what is the identity element for matrix? So that one matrix, that is the element of GL, which when multiplied with some other matrix give us same matrix. What is that matrix? That is an identity matrix. So identity, if multiply right hand side or left hand side of a matrix, does not change the answer. So does identity element belong to the given set? Because identity element we have taken of n cross n order, and also identity element determinant of it is not equal to 0, because the determinant of identity is 1, not is equal to 0, which implies In belongs to the given set, which proves the existence of identity. That means identity exists in the given set. Now for the last property, that is inverse, existence of inverse. Does every element has inverse in the set? So if we take one element A that belongs to general linear group, then its determinant must be non-zero. That is the condition for being in the group. So now if determinant is non-zero, it means A inverse exists. If A inverse exists, that means A into A inverse must be I, or A inverse into A is I. That is the condition that we need for the existence of inverse. We must have some element with which we multiply A to get identity as answer. So here that element is A inverse. So A inverse, does it belongs to the set? Because A is of order n, so A inverse is also of order n, n cross n. And the second thing, determinant. Now what is the determinant of A inverse? Determinant of A inverse is non-zero, because determinant of, how we can say this? Because determinant of A into A inverse is equal to determinant of I. How can we say this? From this, taking determinant on both sides, we get determinant of A into A inverse is equal to determinant of I, which is 1. And what is determinant of A? Determinant we can expand over the product. So determinant of A into determinant of A inverse is 1. So what will be the determinant of A inverse? It will be 1 upon determinant of A. And because determinant of A is non-zero, therefore this is also not 0. If any matrix that is of order n cross n and whose determinant is non-zero, these are the two conditions that must be satisfied to be the member of the set general linear group. So all the four conditions are true, therefore this set is a group, general linear group. That is why we call it. And it is non-abelian. Why? Because the product of matrices is non-commutative. So these are not equal, therefore general linear group is non-abelian. Non-abelian group, right? So now come to the next thing, special linear group. So first of all we write the special linear group. We can write S for simplification. This is the set of n cross n matrices such that determinant of A we can write in short form is 1. This is the definition of S. Now we are going to check whether it is group or not. So first of all we will check closure property. So we take two elements from S. Now if these two elements from S, then determinant of A is 1 and determinant of B is 1, and order of both is n cross n. Now we are going to check whether their product with their composition is also from the same set. To be the element of this set, it must be of order n cross n, which is true. This is of order n cross n because A is of order n cross n and B is also of order n cross n, so their product will be of order n cross n. The other thing about the determinant, so we can write it here. Determinant will be determinant of A into determinant of B, which is 1 into 1 because the determinant of A and B are both 1. So determinant is 1. These are the two conditions, order and the value of determinant. Both are satisfied. Therefore AB belongs to S, which implies closure property hold. Now come to the second property. For second property we don't need to do much. Just we have to write that AB into C is equal to A into BC. That is true for matrices. And now identity. For identity, I work as identity because this belongs to the set. Why? Because this is of order n cross n and determinant of I is equal. So we have the identity element which belongs to S. Why this belongs to S? Because it is of order n cross n, and the second condition, determinant of I is 1, that we know. Also, why this is identity element? Because when we multiply I with A, the answer remains A. Whether we multiply it on left side or on right side, the answer is A. That is why I is the identity element. This is the case why this is identity, and why we call this exist in the set, because it belongs to S under these two conditions. Now the last thing, the inverse. Now what about the inverse? For inverse, if A is some element of S, that means A is of order n cross n and determinant of A is 1. These are the two conditions to be the member of S. Now we are going to check whether inverse of A is the element of this, because inverse of A inverse is the only element that make it identity when multiplied or composed with A. So this is the condition, that is why it is inverse. Now does this belongs to S? For which we have to check both things. As A is of order n cross n, so A inverse is also of order n cross n, that we know from matrix algebra. Now the other thing comes, that is whether the determinant of A inverse 1 or not. So for which we have to check this thing, that is determinant of A into A inverse is equal to determinant of what is I, because A into A inverse is I, which is 1, we know that. Now on the other hand, we distribute determinant over these two matrices. We can write this. Now what is determinant of A? Because determinant of A is 1, being the member of the set S, which has all the matrices whose determinant is 1. So 1 into determinant of A inverse. So what is determinant of A inverse? Determinant of A inverse can be written like this also. This is 1 upon 1, which is 1. So these are the two conditions. One is this, A inverse is of order n cross n, and other is this, this has the determinant 1. So these two conditions make us believe that A inverse belongs to S. So inverse exists and also belongs to the set. That proves the existence of inverse in the same set. Now again we can check this is non-abelian. Again the case is same, that AB is not equal to BA for matrices. Therefore this S is non-abelian, but it is a group because it satisfies all the 4 properties that are necessary, and it is a group but not abelian group.